Hey there. So today I'd like to talk to you about a brief history of nanoscience and nanotechnology. And I do want to give credit to where credit is due. I took a lot of this from the nano.gov/timeline from the nano.gov website. So make sure you read over that because there's more information there that I just didn't have time to cover in this brief lecture. So it's interesting to realize that nanoparticles and nanoscience were in use by craftsmen long before they really understood that what they were doing is making nanoparticles. And one example of this is the Lycurgus Cup, which was created in the 5th century by some Romans. So you can see here there's two photos of the cup, and one is under reflected light and one is under transmitted light. And you can see that it looks like different colors from those two different situations. And in 1990, some scientists were doing research on this important artifact, and they discovered that its interesting color and properties were due to nanoparticles of silver, gold, and copper that were embedded in the glass. Now, this continued to be in use in the 6th through 15th centuries. So, for example, here you see a picture of the stained glass window in Notre Dame. And this was created in the Middle Ages by workers, glass workers, and it uses a metal colloid. Now, a colloid is a mixture in which there's very small particles of one substance that are distributed evenly throughout the substance. And so a metal colloid in the stained glass has metal nanoparticles. In particular, the purple of Cassius, which is this beautiful purple color that you can see in the stained glass window in Notre Dame, is due to the gold nanoparticles that are present in the glass. Also, there were some beautiful lustrous ceramic glazes that were popular from the 9th to the 17th centuries, and these were made by craftsmen in the Islamic world. Now, of course, yet again, they didn't understand that they were creating metal nanoparticles, but they did know that if they added certain metals or ores in specific proportions and then treated those materials to a high temperature heat treatment, that they would get different colors out. And you can see some of the beautiful work that they created. This work was elaborated on in a publication in Materials Today by Heiletag and Niederberger called The Fascinating World of Nanoparticle Research. And they show in particular a shard of pottery. This is the same shard of pottery here from scattered light versus specular reflection. It looks like different colors in different situations. Now I'm going to quote them here. Metallic luster decorations of glazed ceramics appeared in Mesopotamia during the 9th century. These decorations showed amazing optical properties due to the presence of separate silver and or copper nanoparticles dispersed within the outermost layers of the glaze. The example in the figure displays iridescence under specular reflection with shiny blue and green colors. Transmission electron microscopy analysis revealed a double layer of silver nanoparticles with smaller sizes from 5 to 10 nanometers in the outer layer and larger nanoparticles from 5 to 20 nanometers in the inner layer, and the distance between the two layers is constant at about 430 nanometers, giving rise to the interference effects that displayed the example of the different colors under different views shown here. So it's really fascinating and interesting what these craftsmen could do just by tinkering around and figuring out how things looked when they tried different treatments. Now, speaking of that, this is a quote from a New York Times article from 2006. It says, called Antique Nanotubes. All hail the great 17th century nanotechnologist Asad Ullah. Actually, he was a sword maker, one in a long line of smiths who forged the legendary weapons known as Damascus Sabers. The recipe for making Damascus steel was lost at the end of the 18th century, so no one knew the reasons for its remarkable qualities, but an analysis by 21st century researchers in Germany provides a clue. Damascus Sabers, they report in Nature, contain carbon nanotubes. The steel also contains nanoscale wires of cementite, an extremely hard carbon iron compound that were probably formed inside the nanotubes like the filling in a cannoli. And these nanowires give Damascus Sabers another distinctive characteristic, a moire pattern of banding on the steel. So these sabers were actually used to great effect during the Crusades, and they were very sharp and hard and became widely respected and known for that. So if you jump forward a few hundred years, then daguerreotypes were also due to the formation of nanoparticles. In 1839, Daguerre created the first commercially viable photograph, and the chemical bonds in the silver salts are broken when they're exposed to light, leaving pure silver. And Daguerre's process involves coating silver iodide on the film, which is then exposed to light when the photograph's taken, and then the film is developed by heating it over a cup of hot mercury, which bonds with the pure silver ions exposed to the light and forms the nanoparticles. And that creates the image contrast as the nanoparticles scatter light differently from the film. So you can see a daguerreotype here and then an image. The scale bar here is 1 micrometer, so you can see that these nanoparticles that are forming have diameters of, a few hundred nanometers. Now, if you're really interested in daguerreotypes, you need to talk to none other than Joe Pollock, who's a faculty here, and he has a huge collection of daguerreotypes that he'll whip out every once in a while for interested groups, and so that's pretty fascinating. He's also done some research studies on daguerreotypes and the image formation in daguerreotypes, and he was one of the pioneers that led us to understand how this works. Moving forward, Michael Faraday, who you probably know more for his work in electricity and magnetism, as many of you are physics majors, he discovered colloidal ruby gold in 1857. If you remember from a scientific documentary, this was sort of a side project of his. He was set to work to try and understand how the glass makers in other countries were doing such a good job making their glass so that England could be more competitive and make its own glass rather than buying foreign glass. But he was the first to report what later came to be called metallic nanoparticles. And in 1847, he discovered that the optical properties of gold colloids differed from those of the corresponding bulk metal. And this was probably the first reported observation of the effects of quantum size, which might be considered to be the birth of nanoscience. And this is a picture of a colloidal gold with a reddish color. Okay, and we'll talk more about all of that, the science of that, later. Now, the first atomic scale imaging probably came from Erwin Muller in first 1936 and later in 1951 with the invention of 2 different microscopes. Here we see a picture of Muller looking down the column of one of his microscopes there. So Muller's first major contribution to optics was the development of field emission microscopy, and it was made while he was still a graduate student working at Siemens in 1936. And field emission is the emission of electrons from the surface of a conductor subjected to a high electric field. The field emission microscope is lensless, consisting of a sample formed into a sharp needle-like emitter and a fluorescent screen. And then when a field's applied to the emitter, electrons tunnel out of the emitter towards the screen where the contrast occurs due to differences in current densities of the electrons, revealing details about the sample surface. That work that he did in 1936 resulted in a microscope with a spatial resolution of about 2 nanometers, which was truly a revolutionary accomplishment. But then later in 1951-56, he developed another innovative microscope that surpassed the capabilities of the earlier instrument, and it was dubbed the field ion microscope. And that invention had a magnification of 1,000,000 times or more and a resolution of 1/4 of a nanometer, and it made it possible for the first time to obtain clear images of individual atoms and their arrangement on the surface of a sample. So he was one of the pioneers in microscopy that allowed us to get atomic scale imaging. Now, in terms, though, of commercial avenues which have pushed us down towards learning more about nanotechnology, you need look no further than the semiconductor industry. And the birth of that probably happened in 1947 when Bardeen, Brattain, and Shockley developed the first point contact transistor. A little mock-up of that is shown down here, and then here you see the 3 scientists in their lab. There's actually a little bit of controversy about that. The guy sitting in the seat is Shockley, and he was the theorist, not the experimentalist, and he got a little jealous later of the credit that was being given to the other 2, and they had some infighting, but that's another story. But their invention of the transistor has been called the most important invention of the 20th century. And it was developed from a semiconductor material, germanium oxide actually, and it was the first device that could both amplify an electrical signal and turn it on and off, which allowed the current to flow or be blocked. It was small, it generated low heat, it was dependable, and it made possible a breakthrough in the miniaturization of the circuitry. And miniaturization is really what we're about here in our nanoscience and nanotechnology class. It heralded the way of the information age and paved the way for the development of almost every electronic device, from radios to computers to space shuttles. Now, for their discovery, of course, Bardeen, Shockley, and Brattain were presented with a Nobel Prize in Physics in 1956. So these guys did that. Now, interestingly enough, to continue on with some of the information posted on aps.org, which I've quoted just now, the genesis of the transistor emanates, interestingly enough, from a marketing problem. In the early part of the 20th century, AT&T was engrossed in expanding its telephone services across the continent in an effort to beat the competition. The company turned to its research and development arm, Bell Labs, to develop innovations to meet this need. At the time, telephone technology was based on vacuum tubes, which were essentially modified light bulbs that controlled electron flow, allowing for current to be amplified. But vacuum tubes weren't reliable, and they consumed too much power and produced too much heat to be practical for AT&T's needs. Furthermore, as scientists at Bell Labs discovered, transcontinental telephone communication required the use of ultra-high frequency waves, and the vacuum tubes were incapable of picking up rapid vibrations. So they assembled an all-star team of scientists. Shockley headed up the group, and then he selected several other scientists, including Brattain and Bardeen, to work on it. They worked on it for several years, and in 1947 they finally had a successful model that could do everything that they needed it to do. So, fascinating stuff. But the integrated circuit was also an amazing development leading to innovations in nanoscience, nanotechnology, and the information age. Now, Jack Kilby, who's pictured here in a couple of different photographs, he was an American electrical engineer who worked with Robert Noyce, who I'll talk about in a second, in the realization of the first integrated circuit while working at Texas Instruments in 1958. So just a few short years after the development of the first transistor, they were already working on the first integrated circuit. Now, Kilby went on to pioneer military, industrial, and commercial applications of microchips. He headed teams that built both the first military system and the first computer incorporating integrated circuits, and he later co-invented both the handheld calculator, which I know you guys are all grateful for, and the thermal printer that was used in portable data terminals. Now, this guy right here is Robert Noyce, one of the ones that also worked on the first integrated circuit. He came up with his own idea of an integrated circuit about a half a year later than Kilby, but his chip solved many practical problems that Kilby's hadn't. It was produced at Fairchild Semiconductor, a company that he had co-founded, and it was made of silicon, whereas Kilby's chip was made of germanium. Noyce and Gordon Moore later founded Intel in 1968 when they left Fairchild Semiconductor, so you know they're doing okay. Arthur Rock, the chairman of Intel's board and a major investor in the company, said that for Intel to succeed, Intel needed Noyce, Moore, and Andrew Grove, and it needed them in that order. Noyce, the visionary born to inspire, Moore, the virtuoso of technology, and Grove, the technologist turned management scientist. Now, speaking of that, here's Moore and Moore's law. So Moore's law is basically the idea that the density of transistors on an integrated chip should double every 2 years. And that's a basic trend that Moore first observed, but then has kept going for about 50 years. And of course, that's due to a large extent for the reliance on nanotechnology and advancement in nanoscience and nanotechnology. So Gordon Moore, also a key founder of Intel. Now, further microscope advances. The scanning tunneling microscope, or STM, was invented in 1981 by these two gentlemen pictured here, Gerd Bennig and Henrik Rohr, and it was invented at IBM's Zurich lab. And it, for the first time, allowed scientists to see, which means, of course, create direct spatial images of, because seeing implies light, which isn't the case. But anyway, individual atoms for the first time, and they won the Nobel Prize for that in 1986. Now, what the scanning tunneling microscope does, and we'll cover this in more depth later in the course, is it uses quantum tunneling of electrons from a sharp tip to a sample, which is either a conductor or a semiconductor. You bring the sharp tip within just a few nanometers of the sample, and as you might remember from modern physics, some of the electrons will be pulled from the tip to the sample in a current. If you apply a bias voltage in a particular direction, they'll just tunnel through that barrier and come out the other side, which is something that you would never envision happening in classical physics, but is one of the main foundations of quantum mechanics. Now, the atomic force microscope was invented in 1986 to answer some of the technological problems that remained from the scanning tunneling microscope in 1981. The problem with the STM is that in an STM, your samples have to be conductors or semiconductors. But if you want nanoscale images of something that is an insulating material, that's more difficult to do. So in 1986, Binnig, one of the same guys that helped invent the STM, along with some new people, Quate and Gerber, invented the atomic force microscope, and that has the capability to view, measure, and manipulate materials down to fractions of a nanometer in size, including the measurement of various forces intrinsic to nanomaterials. And how that works, there's just briefly, we're going to talk more about this later, but in the image that you see here, there's a laser beam that reflects off the back of a cantilever, and on the bottom of the cantilever there's a very sharp tip. Now you move the cantilever and tip across the surface, and then you can track the motion of the tip across the surface by bouncing the laser beam off the back of the cantilever and onto a mirror and then onto a photodiode which tracks it. And you operate it in a feedback loop, and you keep the position of the laser kind of in the center, moving the tip up and down to keep that laser in position. And then you track how you have to move that tip, and you create a little topo map, a little topography map of what your surface looks like. So that's pretty interesting. We're going to talk a lot about carbon materials in this class later. Two of the most notable of those are, of course, Buckyballs and nanotubes, and those were discovered in 1985 and 1991. Now, a buckyball is a carbon-60 and then also some carbon-70 and other molecular weights there. But what happens is they're arranged in kind of a soccer ball arrangement. There's a cartoon of what that might look like over here with sticks representing the bonds in between the carbons, where the carbons are the little balls there. And the team was awarded, Croteau, O'Brien, Curl, and Smalley, that team, was awarded the Nobel Prize in 1996 for chemistry for the discovery of this. They were actually looking for things in astronomy, and it was kind of an accident that they happened upon the buckyball, but it was a very happy accident for all of them. Now, Sumio Iijima of NEC is actually credited with discovering carbon nanotubes. Carbon nanotubes is basically you have a sheet of graphite, which is carbon arranged in sort of a hexagonal pattern, and then you roll that sheet up into a tube. Now, there's images of what those look like, sort of a little forest of nanotubes down here at the bottom right, and some nanotube spaghetti down here at the bottom right. Iijima shared the Kavli Prize in Nanoscience in 2008 for the advance and other advances in the field. And carbon nanotubes like buckyballs are entirely composed of carbon, but they have a tubular shape. Now, carbon nanotubes have some pretty amazing properties. They're very, very strong. They exhibit a high tensile strength. They can either be electrical insulators, semiconductors, or conductors, depend upon their chirality, which means how you roll the tube up. So that's a pretty fascinating property. In the conducting way, they are basically nanoscale wires, which is really valuable for the study of nanoscience and in nanotechnology in the application. And they have very high thermal conductivities, among other really fascinating properties of them. Like I said, we'll talk more about those later, so look forward to that. Now, other notable events from the history of nanoscience that are noted on the nano.gov timeline include, but are not limited to, in 1985 at Bell Labs, they discovered colloidal semiconductor nanocrystals, or quantum dots, which you might have heard, and they won the Kavli Prize in Nanotechnology in 2008 for that. In 1989, Eigler and Schweitzer at IBM's Almaden Research Center actually spelled out the IBM logo with 35 individual xenon atoms, and they did this using a scanning tunneling microscope. You might remember that. It's pretty iconic in the field of nanoscience and nanotechnology, that beautiful image of the IBM logo spelled out in atoms. In 1999, at Cornell University, researchers Ho and Lee probed secrets of chemical bonding by actually assembling a molecule from the constituent components with a scanning tunneling microscope. So they brought atoms together and made their own molecule that way, which is pretty fascinating. And then at Northwestern University, also in 1999, dip pen nanolithography was invented. So basically there you have an array of AFM tips, you dip those in the material that you want to write, and then you use the AFM in a pattern, moving it in a pattern to write it out. And this led to manufacturable, reproducible writing of electronic circuits, as well as patterning of biomaterials for cell biology research, nano-encryption, and other applications. And then finally, I'm going to stop here. In 2000, President Clinton launched the National Nanotechnology Initiative, the NNI, to coordinate federal R&D efforts and promote U.S. competitiveness in nanotechnology. And Congress funded the NNI for the first time in 2001. And the subcommittee of the NSTC was designated as the interagency group responsible for coordinating the NNI. What this led to was an explosion of research in nanotechnology and nanoscience that led to a lot of the innovations and products that you see on the market today, just due to the increase in funding of nanoscience and nanotechnology research from the government. So I highly encourage you to read in chapter 1 of your textbook about, maybe in a little bit more depth, some of the advances and some of the history of nanoscience and nanotechnology in chapter 1. And also to go to the website nano.gov/timeline and read some of the ones that I just didn't have time to go over in this lecture. I hope you enjoyed it, and I'll see you next time.